April 7, 2001 was not a date that anyone expected to remember for long. A Delta II rocket left Cape Canaveral carrying a spacecraft nobody celebrated. No astronauts aboard, no flagship status, no speeches from the president. Total budget, $297 million. Modest by the standards of planetary science. 3 instruments packed into 376 kilograms of carefully engineered hardware. The spacecraft was named Mars Odyssey as a tribute to Arthur C. Clarke's vision, but Clarke had imagined voyages with wonder. This one launched to map minerals. Its mandate was a 2-year science mission above a cold and dusty planet. The number 376 kilograms does not sound like much for a spacecraft, but every kilogram launched to Mars represents roughly $10,000 of fuel costs alone. Keeping mass low was not an aesthetic preference. It was a financial and physical necessity. Engineers designing Odyssey made hundreds of trade-offs between capability and weight throughout. The relay system that proved so essential survived those cuts because it weighed almost nothing. A few kilograms of receiver hardware and the software to manage data storage and retransmission. That restraint around an overlooked component created indispensable planetary infrastructure. Nobody standing at the launch pad expected to still be tracking it in 2025. The number that haunts JPL today is not measured in light years or discoveries. It is measured in kilograms. The propellant left aboard a 24-year-old orbiter. When that number reaches 0, something essential in Mars exploration will break. Not with drama, not with headlines, quietly, the way infrastructure always ends. To understand what that silence costs, the story has to begin at aerobraking. 7 months after launch, on October 24, 2001, Mars's gravity caught the spacecraft. The insertion burn slowed Odyssey enough for Mars to claim it as a new satellite. What followed was 76 days of something engineers call aerobraking. Each orbit dipped the spacecraft into the very top of the Martian atmosphere. Friction on every pass shaved velocity, gradually collapsing the elliptical orbit. Engineers at JPL had modeled the Martian atmosphere carefully before the mission. Their models predicted how much braking each orbit would provide on average. What the models slightly underestimated was the atmosphere's cooperative density. The braking was marginally better than predicted on hundreds of consecutive passes. Better braking meant the engine needed to fire slightly less often to correct the orbit. Every spared engine firing preserved a gram here, a few grams there per session. 76 days of marginal savings accumulated into something nobody had counted. By January 2002, Odyssey settled into a 400-kilometer circular orbit and began work. The propellant cushion from aerobraking was filed away and essentially forgotten. Philip Christensen at Arizona State University had spent years designing Themis. The instrument's full name was the Thermal Emission Imaging System. Its function was to read heat signatures off the surface of a distant world. Rock absorbs solar energy through the Martian day and releases it after sunset. Different minerals release stored heat at measurably different rates in the dark. Basalt cools at one pace, clay at another, unaltered volcanic rock at yet another. By mapping those cooling signatures across the entire surface, Themis identified minerals. Christensen's central argument was that water permanently changes the chemistry of rock. Liquid water reacts with basalt to form clay minerals that survive for billions of years. Water-altered rock and unaltered rock have completely different thermal emission profiles. Find the altered chemistry from orbit, and you find where the ancient water once flowed. Themis was his career-long argument, made physical in germanium lenses and detector arrays. The first major discovery came not from Themis, but from a companion instrument called GRS. The gamma-ray spectrometer detected nuclear emissions from elements in the Martian soil. When cosmic rays strike hydrogen atoms in the ground, they produce a specific energy signature. In 2002, GRS data showed enormous hydrogen concentrations near both Martian poles. The concentrations extended into lower latitudes and traced complex geographic patterns. The only substance that produces those readings at that scale was water ice in the soil, not surface frost that comes and goes with seasons. Permanent ice mixed into the dirt. The discovery overturned decades of scientific consensus about what Mars was like today. Mars had been classified as too cold and too dry for substantial water to survive anywhere. Odyssey's maps revealed water ice deposits spanning millions of square kilometers below ground. The scientific debate that followed was intense, as it always is when consensus breaks down. Some researchers argued the hydrogen signatures could come from hydrated minerals instead. Others pointed to the depth profiles and concentration gradients as conclusive for ice. The argument ended definitively on May 25, 2008, when Phoenix landed in the northern plains. Christensen's team had helped select the landing site based on Odyssey's hydrogen maps. Phoenix's robotic arm scraped a shallow trench on its second day and exposed something white. That white material began sublimating within 4 Martian days as the sun warmed the surface. It was water ice, exactly where the 2002 data had predicted, exactly at the predicted depth. Themis, meanwhile, was conducting its own systematic investigation of Martian mineralogy. The instrument found ancient hydrothermal deposits across several regions of the southern highlands. Hydrothermal systems require liquid water, volcanic heat, and sufficient time for chemistry. Mars had all 3 conditions for hundreds of millions of years in its early history. Where those systems existed, the mineral record shows evidence of sustained liquid water presence. Themis also cataloged large regions where olivine had survived unaltered in the ancient rock. Olivine dissolves in liquid water and vanishes from the rock record within just millions of years. Its survival meant those areas had stayed dry since before the solar system reached half its current. The instrument was distinguishing between wet ancient Mars and dry ancient Mars, patch by patch. The Phoenix mission that eventually confirmed the ice was not inevitable. It required advocacy. Scientists had to argue for a dedicated lander targeting Odyssey's hydrogen anomaly specifically. Budget pressures and skeptical reviewers stood for years between the discovery and its confirmation. Phoenix launched in August 2007 and touched down in the North Polar region on May 25, 2008. The white material the robotic arm exposed disappeared in 4 days, exactly as water ice would. Without Odyssey's maps pointing to that specific region, Phoenix would have landed somewhere else. The confirmation story is inseparable from the detection story. Both belong to this one spacecraft. Then it found hematite concentrated in a region called Terra Meridiani in the equatorial zone. That crystalline hematite form typically precipitates from liquid water inside sedimentary layers. Scientists flagged the deposit and began arguing for a rover landing to investigate it directly. Opportunity landed at Terra Meridiani in January 2004 and found hematite concretions everywhere. The science team called them blueberries. They had formed inside ancient wet sedimentary layers. Opportunity spent 15 years investigating the ancient wet environment Odyssey had identified. Gale Crater was selected for Curiosity's 2012 landing, partly because Themis showed clay minerals. Clay minerals require prolonged contact with neutral pH water, the chemistry hospitable to life. Jezero Crater, where Perseverance landed in 2021, showed orbital evidence of an ancient river delta. 3 of the most productive Mars surface missions landed exactly where Odyssey's data pointed. The 2-year mapping mission, with a modest budget, was writing Mars's exploration roadmap for 2. The Mars Reconnaissance Orbiter launched on August 12, 2005, and arrived at Mars in March 2006. It carries a camera called HiRISE that resolves objects 30 centimeters across from orbit. It also carries relay hardware and began supplementing Odyssey's relay capacity from its arrival. For nearly 2 decades, the 2 spacecraft have shared relay duties over the Martian surface. When one is in a poor orbital geometry for a particular rover, the other often compensates. The system works because 2 orbiters have different orbital periods and phase slightly differently. Losing one reduces both capacity and the redundancy needed when orbital geometry turns unfavorable. But the instrument that would define Odyssey's legacy was not a science instrument at all. Engineers included a radio relay receiver in the design almost as an operational convenience. Future surface missions would need to communicate with Earth, and an orbiter could help with that. The calculation was simple. A rover's small antenna transmitting directly to Earth performs poorly. Signal strength falls with the square of distance. 200 million kilometers is a brutal distance. Direct transmission from the Martian surface achieves perhaps 10 kilobits per second maximum. A spacecraft 400 kilometers above is close enough to receive a rover's transmission at full power. Odyssey stores the data in its onboard memory and retransmits it to Earth using its larger antenna. Through the relay, that same rover achieves data rates approaching 2,000 kilobits per second, 200 times faster. Not a marginal gain, but a transformation in what surface science becomes. Without a relay, a rover sends perhaps one compressed image back to Earth per Martian day. Through Odyssey overhead, a rover sends hundreds of images and thousands of measurements per. Spirit and Opportunity landed in January 2004 and routed their data through Odyssey from day one. The twin rovers returned science volumes that would have taken decades through direct transmission. Opportunity operated for 15 years and sent back more than 200,000 images across that time. The overwhelming majority of those images passed through Mars Odyssey before reaching Earth. Curiosity landed in Gale Crater on August 6, 2012, and Odyssey was directly overhead during descent. The sky crane had never been attempted. A rocket crane hovering while lowering a 1-ton rover. Engineers called it 7 minutes of terror because every step required a different system to work. Curiosity landed, and Odyssey was the spacecraft that confirmed the landing had succeeded. Those first Gale Crater images, sent minutes after touchdown, passed through an aging orbital relay. By the time Perseverance landed in Jezero Crater in February 2021, the dependency had become total. Odyssey was relaying 85 to 90% of all data from every active mission on the Martian surface. The oxygen production experiment, the Ingenuity helicopter flights, the ancient Delta rock samples. All of it passed through a spacecraft that was supposed to map minerals for 2 years and stop. The engineers who added the relay as a convenience had inadvertently built planetary infrastructure. Nobody planned for this outcome. Nobody could plan for missions that did not yet exist at all. Infrastructure never announces itself as infrastructure until someone tries to operate without it. In 2012, the year Curiosity landed, a JPL conference room audit changed the mission's entire. Mission managers reviewed the propellant budget and found a number larger than any estimate had. The aero-braking savings from 2001 had been compounding quietly in the background for 11 years. Every correction that burned slightly less than worst-case models had quietly preserved small. 11 years of those reserves had accumulated into something real. Years of additional operational. A spacecraft built for a 2-year mission in 2001 had enough propellant remaining to operate past. The extension was approved, then approved again and again, as the fuel outlasted every projection. Each extension deepened the relay dependency that the Mars surface program had quietly built around. By 2024, controllers tracked propellant not in monthly allocations, but in individual thruster. Holding the 400-kilometer orbit requires regular small burns to fight drag from the thin upper. At 400 kilometers, the atmosphere seems negligible, but exerts enough drag to matter across months. Without corrections, drag lowers the orbit gradually, shifting relay windows and degrading data. Engineers estimate remaining fuel sustains operations through 2025 or the opening weeks of 2026. After the fuel is gone, the orbit drifts uncorrected, and relay windows become steadily less. Eventually, the atmosphere that helped during aerobraking in 2001 will finish the work it began then. The spacecraft descends into denser air, heating begins, and the orbit converts to a re-entry path. Mars Odyssey will return to the planet it studied for 24 years from 400 kilometers above. There is poetry in that trajectory, though the poetry contains a genuinely serious operational. When Odyssey stops relaying, the surface does not go silent. It goes narrow in one specific way. Curiosity and Perseverance retain their direct antennas and will continue sending data to Earth. The Mars Reconnaissance Orbiter, launched in 2005, will also continue providing relay services. The European Space Agency's Mars Express contributes relay capacity when its geometry allows. 3 relay-capable orbiters working together provide something that 2 cannot fully replace. Each orbiter passes overhead at different times, spreading relay windows across the Martian day. Removing one creates gaps, stretches when rovers must queue data and wait for the next available. Data that currently arrives within hours of collection will take days to queue during gap periods. Science teams operating Curiosity and Perseverance have built their operational tempo around current. Drill schedules, sample sequences, drive distances per sol, all calibrated to existing relay. Reducing that throughput forces fundamental changes in how surface operations are planned and run. NASA refers to this formally as the relay gap in its long-range mission continuity planning. The gap is not hypothetical. It is a documented engineering consequence with a precisely known. The Mars Sample Return mission that NASA and ESA have planned for the 2030s depends on solving this. Perseverance has been caching rock cores in titanium tubes since 2021 across the floor of Jezero. Those samples are the most carefully selected collection from an ancient, potentially habitable. A sample retrieval lander must land, deploy a fetch rover, and load the sealed tubes into a rocket. The Mars Ascent Vehicle launches from the surface, the first rocket ever fired from another planet. An Earth return orbiter rendezvous with the capsule and carries it back across interplanetary space. Every step requires continuous telemetry, real-time confirmation, and reliable relay infrastructure. Build that chain without solving the relay gap, and the most expensive science mission in history. 2 relay satellites under NASA's Next Mars Orbiter program are in development specifically to close. If funded consistently and launched by 2028, they arrive before relay capacity falls to a critical. Modern relay hardware would achieve rates that make Odyssey's 200 times improvement look modest. Technology is not the constraint. The documented need, engineering capability, and cost estimate. What is uncertain is sustained political will to fund infrastructure across multiple budget cycles. Infrastructure is always vulnerable to the argument that something more exciting deserves priority. A relay satellite does not land on Mars, drill rock, or generate a single press conference. It orbits, receives surface transmissions, and quietly forwards them to scientists waiting on Earth. This is exactly what Mars Odyssey has done since 2002, without one headline dedicated to the relay. A meeting happens regularly at JPL that receives no public coverage and produces no press releases. Engineers review every health parameter of a spacecraft approaching the end of its propellant. Battery capacity degraded after 24 years of charge cycles in Mars orbit, still within. Solar panel efficiency reduced by radiation and micro-impacts over 2 decades, still generating. Thruster performance nominal, fuel remaining tracked to the kilogram. Relay windows modeled per. Every meeting is simultaneously a mission status review and a countdown nobody in the room states. The spacecraft keeps exceeding expectations with each review, and the fuel number keeps falling. In 2023, the operations team reduced orbital station-keeping burn frequency to preserve propellant. The orbit drifts from optimal relay geometry, reducing efficiency on certain passes as a result. Rover teams were briefed on the trade-off and accepted the reduction as the most rational choice. An Odyssey at 85% relay efficiency burns less fuel than one at 100%, so it lasts. These decisions live only in operational logs and technical briefings that never reach any public. Quiet trade-offs between a mission's remaining life and the urgent needs of the missions that depend. The Voyager missions offer a contrast that clarifies what makes Odyssey's situation fundamentally. Voyager 1 and Voyager 2 launched in 1977 on 4-year missions to the outer solar system. In 2025, both are still transmitting data from the heliosphere's boundary 48 years after their play. Their propellant ran out decades ago, but momentum in the near vacuum of interstellar space has no. They coast at roughly 17 kilometers per second and will continue coasting with essentially nothing. Mars Odyssey orbits inside an atmosphere, and atmospheric drag is a debt that orbital physics. There is no coasting for a spacecraft in low planetary orbit. Physics requires continuous. The engineers currently operating Odyssey are not those who designed and launched it in 2001. They learned this spacecraft from mentors who learned it from the original team, which has since. Knowledge about a spacecraft operating for 24 years accumulates into something substantial. Anomaly procedures, orbital correction techniques, relay window protocols, thermal management edge. The 2012 safe mode crisis generated one concrete example of accumulated knowledge becoming. In September 2012, Odyssey went dark after an attitude control fault triggered the automatic safe. Curiosity had landed 4 months before and was routing its first science data through Odyssey. Safe mode cut that connection and left the newest rover on Mars running on degraded direct. JPL engineers traced the fault to a timing error, built a software patch, and transmitted it upward. 22 minutes of silence separated transmitting the fix from learning whether the spacecraft. Odyssey recovered, and the incident produced a flight rule that is still active on the spacecraft. The engineers who wrote that rule, from hard experience, have since retired or moved to different. But their rule still governs every command sequence sent to Odyssey during elevated solar activity. This is what long-duration spaceflight looks like inside. Accumulated procedures protecting aging. Current operators understand failure modes and thermal behaviors that no single document fully. They know which commands need extra verification and which geometries stress the attitude control. That knowledge has nowhere to go when the mission ends, except into documents nobody must ever read. There is something that engineers running long missions rarely discuss in any professional setting. The spacecraft becomes part of the daily working rhythm in ways that resist any precise. It transmits every day, relay windows arrive on schedule, and health telemetry comes back nominal. It fails in small ways occasionally, and the team resolves it, and the daily rhythm continues. Eventually, the rhythm stops, and the monitors show only empty frequencies where data used to arrive. JPL will reassign the frequency to a newer mission and repurpose the control room for something. The operations team disperses to other missions, and the spacecraft orbits silently for additional. Without burns, the orbit decays until the atmosphere claims what aerobraking started back in 2001. The entry will happen on one of the roughly 5,000 daily orbits completed since the fuel ran out. It happens somewhere over the planet, probably on the night side, with no asset positioned to watch. Mars absorbs the spacecraft that studied it for 24 years without marking the moment at all. What remains is not nothing. It is 2.5 decades of documented and irreplaceable polar maps updated through 24 Martian seasonal cycles, showing where and how deep the ice. Mineralogy surveys of the entire surface at resolutions adequate for landing site pre-selection. Climate records spanning 24 Martian years, the longest thermal dataset for any world. That dataset is the calibration baseline for every atmospheric model and every climate study after. When scientists debate whether early Mars held liquid water for millions or billions of years, this Phoenix confirmed the water ice Odyssey found. Opportunity investigated the hematite Themis had. Curiosity and Perseverance landed in sites Themis mineral surveys helped select as scientifically. The science that made international news unfolded on the surface, carried out by rovers everyone. The foundation that made it possible was built by a spacecraft most people have never heard of. In October 2021, NASA marked the mission's 20th year in Mars orbit with a brief acknowledgement. The spacecraft had transmitted more than 1 petabyte of scientific data across those 2 decades. 1 petabyte is 1 million gigabytes. Reading it at home speeds takes roughly 1,000 years. A standard 2-hour film in high definition requires roughly 4 gigabytes of storage to hold. 1 petabyte of film would require 57 years of continuous watching to finish, without any. Odyssey transmitted that entire volume while funded and designed as a 2-year mineral mapping. The legacy is not any single discovery, though the water ice find alone justified the full program. The legacy is continuous accumulation from a platform that kept working when it had no reason to do. Engineers use the term graceful degradation to describe how reliable systems should ideally fail. Rather than sudden collapse, reliable systems preserve as much function as physically possible. Mars Odyssey has been demonstrating graceful degradation across 2 full decades of continued. Sensors failed, and software compensated by routing measurements through backup detector channels. Thermal management adapted as reflective coatings aged, and the spacecraft's overall thermal balance. The mission absorbed relay duties nobody planned for and executed them for 2 decades without. Most hardware grows progressively less capable as components age and tolerances drift over. This spacecraft grew progressively more essential with each year it operated beyond its intended. The engineers who assembled Odyssey at Lockheed Martin in Denver were building a mineral mapper. They were not building the communications backbone of a 20-year Mars surface exploration. The universe repurposed their work, as it tends to repurpose anything built well enough to last. When Odyssey stops transmitting, the relay gap forces a question that has been deferred for 2. Why does planetary exploration consistently underfund the infrastructure that makes surface science? The pattern repeats in the history of robotic exploration. Missions get funded as individual science. Each mission justifies its cost on its own merits, without accounting for the infrastructure beneath. When Odyssey was designed, nobody asked what would happen to Mars surface operations when the surface missions that would depend on it, did not exist yet, so the question seemed premature. By the time dependency was fully documented, the aging infrastructure was already nearing its end. 2 relay satellites now in development represent the first deliberate attempt to close this. Funded consistently and launched by 2028, they arrive before the relay capacity falls to a critical. The argument for funding them is not theoretical. It is encoded in 24 years of operation. It shows what Mars surface exploration looks like with excellent relay capacity behind every. It shows what 2012 looked like when that capacity went dark for 6 weeks and a rover had to whisper. It shows what happens when fuel runs out and no replacement orbiter waits above to keep relaying. Odyssey made the case for its own successor through 2 decades of operations nobody had originally. Whether that case is heard before the relay gap opens is about institutional memory and stated. Not about technology, that exists. Not about scientific value, that is thoroughly and repeatedly. About whether organizations responsible for Mars exploration treat infrastructure as a first class. We have a tendency on Earth to notice infrastructure only at the precise moment it fails. Roads get repaired after they crack. Bridges get reinforced after inspections reveal hidden. The Roman road network was the most sophisticated infrastructure system the ancient world had. 400,000 kilometers of paved road connected 70 million people across 3 continents. When the Western Empire fragmented in the 5th century, road maintenance funding collapsed almost within 2 generations. Roads that had endured for 5 centuries crumbled to impassable tracks. The cities those roads connected contracted inward. Trade routes collapsed, and knowledge transfer. Europe spent roughly 1,000 years rebuilding infrastructure that had taken centuries to build. The lesson is not about Rome specifically. It is about what neglected infrastructure ultimately. What we are building at Mars is embryonic and entirely dependent on a handful of aging orbiters. Surface exploration at Mars works because orbital infrastructure made it scientifically productive. Without it, rovers are isolated instruments transmitting data fragments through geometrically. With it, Rovers become nodes in a network, returning comprehensive observations at genuinely useful. Odyssey proved that proposition across 24 years of operations nobody planned for and all. Its retirement will not end Mars exploration. The rovers continue. MRO continues. Mars Express. But it narrows the bandwidth through which the surface speaks to Earth. And narrowed bandwidth, the questions Mars can answer about water, life, and terrestrial planet history do not get smaller. The capacity to receive those answers shrinks when Odyssey falls quiet over the Martian atmosphere. That is the consequence of launching a spacecraft in 2001 without planning for what happens when it... Not catastrophe and not total silence. A narrowing that is gradual, documented, and entirely. We are what we choose to sustain. And sustaining something over decades reveals what we actually. For 24 years, Odyssey was sustained beyond every expectation by engineers who believed it. The question is whether the institutions responsible for Mars exploration will say the same about. The spacecraft cannot answer that from its orbit. That answer only exists in budget rooms on Earth. Controllers at JPL operate Odyssey through a deep space network antenna complex. The primary station used for Mars contact is Goldstone in the Mojave Desert of California. Canberra, Australia, and Madrid, Spain provide additional coverage as Earth rotates through sessions. A contact session with Odyssey lasts roughly 30 to 40 minutes, depending on orbital geometry. During that window, stored relay data uploads, health telemetry downloads, and commands are sent. The session ends as geometry degrades, the data is processed, and rover teams receive their science. This quiet daily exchange has repeated thousands of times since January 2002 without public notice. The missions that will follow Odyssey into Mars orbit face a different kind of challenge. They must be designed from the outset as infrastructure, not just as individual science platforms. The relay gap reveals a flaw in how planetary exploration projects are conceived and funded. Science drives approvals and headlines. Infrastructure funding follows only when crisis has arrived. The 2 relay satellites now in development were approved specifically because Odyssey is ending, not because planners looked ahead a decade and funded what would eventually be needed. The lesson of Odyssey is also a lesson about how humanity builds for the long term in space. We do not yet plan across generations the way the problem requires. We plan in budget cycles and administration terms and mission lifetimes measured in years. Building a civilization on another planet requires planning in centuries, not fiscal quarters. Odyssey lasted 24 years, and in doing so, became something nobody planned for it to become. The infrastructure it built lasted 24 years and became irreplaceable. What we choose to build next will define what the 24th year of the next program looks like. By April 2026, that question is no longer abstract. The answer is being written in real time. And the answer, so far, looks nothing like the clean institutional planning that Odyssey deserved. The first thing that happened between 2024 and 2026 was not construction. It was another loss. On December 4, 2025, NASA's MAVEN orbiter sent its last data transmission from Mars orbit. MAVEN had been studying the Martian atmosphere since 2014 and had doubled as a relay satellite. 2 days after that final transmission, radar stations on Earth detected something alarming. The spacecraft was tumbling uncontrollably, spinning without any ability to correct its orientation. MAVEN had lost the ability to determine which way it was pointing in relation to the sun. Without orientation, its solar panels could not track power, and its antennas could not find Earth. NASA attempted contact through every DSN antenna available and got no response for weeks. Mars then entered solar conjunction, the period when the sun blocks all radio contact entirely. When Mars re-emerged in January 2026, the agency tried again and received nothing back from MAVEN. Louise Proctor, director of NASA's Planetary Science Division, delivered the assessment directly. Recovery was very unlikely, she said, and the agency was preparing to accept the mission as lost. Maven had enough fuel to hold its orbit until 2030. It was not hardware failure that ended it. A software or sensor fault had converted a fully fueled spacecraft into a silent, tumbling object. The loss removed another relay node from a network that was already watching Odyssey decline. Mars Odyssey, MRO, and the European ExoMars Trace Gas Orbiter absorbed Maven's relay share. Rover science teams redistributed transmission schedules across the remaining 3 orbiters. The system held, but the margin that had existed before December 2025 no longer existed afterward. 2 orbiters were now doing the work that 4 had shared just 12 months earlier. The second development between 2024 and 2026 was political rather than technical in origin. In the summer of 2025, Congress passed legislation known informally as the One Big Beautiful Bill. Buried inside that legislation was a line item that almost nobody in the press had noticed. $700 million earmarked specifically for a Mars telecommunications orbiter. The legislation required NASA to award the contract before September 30th, 2026. It also required the selected spacecraft to launch no later than the end of calendar year 2028. The funding was real, and the timeline was a legal obligation, not a planning target or a study. The primary commercial candidate was Rocket Lab, the small satellite company based in New Zealand. Rocket Lab had proposed a spacecraft called the Mars Telecommunications Orbiter, or MTO. Rocket Lab framed the MTO as invisible infrastructure for the next generation of Mars missions. Those exact 2 words, invisible infrastructure, were the lesson Odyssey had been demonstrating. The legislation appeared tailored to benefit Rocket Lab, according to multiple industry sources. Drafting errors in the bill had accidentally opened the competition to other contractors as well. In early 2026, NASA posted a pre-solicitation seeking industry feedback on mission requirements. The objectives document was initially marked controlled and withheld from the public record. After reporting on its contents surfaced, NASA released the 24-page document publicly. Inside, 4 top-level objectives covered communications only. No science requirement appeared. The spacecraft must relay data between Mars-based assets and Earth through at least 2035. It must provide Doppler, range, and timing support for navigation of Mars surface missions. For the first time in planetary exploration history, a Mars relay was being designed as Relay First, not a science platform carrying relay hardware as an operational convenience in the instrument bay, not a mineral mapper with a receiver added so future rovers could talk to Earth more efficiently. A relay satellite, conceived as relay, funded as relay, required by law to function as relay. This was the institutional shift that Odyssey's 24 years of operation had been demanding. The third development came from a different direction and carried a different kind of significance. On November 13, 2025, NASA launched a mission called Escapade from Cape Canaveral, Florida. The name stood for Escape and Plasma Acceleration and Dynamics Explorers, 2 small spacecraft. Their mission was to study how solar wind strips atmosphere from Mars across deep geological time. The 2 spacecraft launched into a loiter orbit near Earth, rather than heading directly toward Mars. In fall 2026, when Earth and Mars align, Earth's gravity will slingshot them toward the planet. They are not relay satellites and carry no hardware designed to address the communications gap. But every spacecraft in Mars orbit adds geometry and coverage windows to the communications network. Escapade will contribute navigation support, even if relay remains secondary to its science mission. What mattered most about Escapade in the context of this story was the timing of its launch. It entered space 1 month before Maven tumbled and joined a network already under growing stress. The Mars Relay Network, entering 2026, looked nothing like what mission planners had imagined in 2020. Maven was gone. Odyssey was running on months. MRO was 20 years old, with more margin left. The ExoMars Trace Gas Orbiter, a joint ESA and Roscosmos mission, continued providing backup relay. But Russian involvement had been complicated by geopolitical realities that emerged after 2022. The network that was supposed to be robust had become fragile within the span of a single year. Into that fragility came the $700 million mandate, the Rocket Lab proposal, and the 2028 deadline. The contrast with how Odyssey's relay capability originally emerged could not be more complete. Odyssey's relay emerged from accident, an overlooked receiver on a mineral mapping mission. The Mars Telecommunications Orbiter emerged from legislation, a senator's earmark in a budget bill. One was built without anyone planning to need it and became irreplaceable across 2 decades. The other is being built because everyone now understands exactly how much it will be needed. Odyssey proved the value through operation. The MTO is funded because that proof now exists. Rome did not build its roads because anyone predicted a unified network would prove valuable. Roads got built because specific generals needed to move armies to specific places efficiently. The network emerged from accumulation rather than design, outlasting everyone who built any part. The Mars Relay Network followed the same accidental logic across 25 years of development. Odyssey's receiver was a convenience. MRO's relay was an afterthought. Maven's was supplementary. None were built as infrastructure, and all became infrastructure through the simple act of lasting. The Mars Telecommunications Orbiter will be the first exception to that pattern in program history. It is being built as infrastructure deliberately, funded explicitly, required by law to relay data. Whether it launches on schedule, whether it performs as specified, whether it survives long enough. Those questions get answered after 2028 by engineers who have not yet been assigned to the mission. The fact that it is being built at all represents something Odyssey's retirement made unavoidable. That argument could not be dismissed after 20 years of proof that Odyssey alone had provided. 24 years passed between launch and the moment funding for its replacement became mandatory. It is not a satisfying timeline, and not one that careful long-range planning would have produced. But it is the actual timeline, and it holds a lesson extending well beyond Mars or relay satellites. The things we depend on most are recognized last, funded last, replaced only when losing them hurts. Odyssey was invisible while it worked, and indispensable only after it started dying. The next mission that becomes invisible while working will teach this lesson to another generation. Unless the people responsible for Mars exploration remember what they are watching happen right now. In April 2026, Odyssey is still up there, still orbiting, still relaying whatever the fuel allows. The contact sessions are shorter now, and the relay windows less predictable than a year ago, but the data still comes through. The rovers still transmit, and the network still functions. For a few more months, the spacecraft that launched on an unremarkable morning in April 2001 is still doing exactly what nobody planned for it to do, and everyone came to depend on it doing. That is not a footnote to the story of Mars exploration. That is the story of Mars exploration. Thank you for staying with us until the very end of this journey through deep time. If this exploration moved you, subscribe and stay for the next ancient chapter. Your curiosity is what keeps these lost worlds alive.